Possibly one of the biggest challenges of integrals is just knowing when to apply them. So if we're finding the total distance over an interval, we would take the integral of the absolute value of velocity, because if we're headed to the left or the right, we want all of those distances to end up being positive distances. Whereas if we're finding displacement and not the total distance, then we would just take the integral of velocity. This concept translates to any accumulation function. So if we're being given the rate of fish being caught in fish per hour is r of t, then the amount of fish that we catch from 1 to 4 hours is just found by the integral from 1 to 4 of that rate. Typically in real world problems, I don't have to worry about the absolute value because what I'm talking about can't be negative. So in this case, the amount of fish or the fish that I caught per hour can't be negative. I can't catch a negative amount of fish. So usually I don't have to worry about that. But with distance, if we have that negative being left and positive being right, something like that, then we do have to consider the absolute value for totals. Next, we have the average value of a function over AB, which is similar to previous, but we're dividing also by 1 over b minus a. So for example, if we're trying to find the average velocity over the interval 1 to 3, we would take 1 over 3 minus 1 of the integral from 1 to 3 of v of t, which is really the same as if I did integrate velocity, I get position. And so this is really a slope, or the average rate of change of position is the same as the average velocity. Because integrating is really just finding the antiderivative, in particle motion, if we're given the velocity or acceleration, we can use it to work backwards to find position. Or if we're given the acceleration, we can integrate to find velocity. For example, if we're given the velocity of a particle and then told a value, in this case the initial position, and then trying to figure out the position at another value, I would want to integrate velocity to find position. I would have that plus c, and that's where my value comes in, that my position at 0 seconds is 3, so I'd plug in 0 for my time, my position being 3, and I get that my c value is 3. So that would tell me this is my position function, and then I can plug in t being 1 to figure out the position when time is 1. We use integrals to solve differential equations. So for example, if we had a derivative that was 3x over y, I would need to multiply both sides by y, and move my dx to the other side as well, and then integrate both sides in order to get y by itself. Also, sometimes functions are just defined by an integral, so g of x could be the integral from 2 to x of f of t dt. It's really important if we're talking about something like this to note that g prime of x, so if we're taking the derivative of an integral, remember we would be using that second fundamental theorem and saying that g prime of x is actually the same as f of x. So let's try some examples. I do want you to go ahead and pause the video, read this first example, and try it on your own. So because we're talking about total distance traveled, we're looking to find the integral from 0 to 16 of the absolute value of velocity. And in this case, I don't really have to worry about the absolute value because it's all above the x-axis. But if I did have something below, I would give it a positive area instead of a negative one so that I'm finding the total distance. But for each piece here, I'm just using formulas to find the area of the triangle, the area of the rectangle, the area of the trapezoid. Make sure that you're being careful about what numbers they're counting by 2s for the x's and 30s for the y's. So be careful there, but you should end up with 780. Here's our next example. Again, pause the video, try it on your own. So for g of -3, we're just plugging in -3 in for both x values here. So on the left, I just have 2 times -3, but on the right, I'm looking at that integral from 0 to -3 of the graph that I've been given. First, because these bounds go from greatest to least, I need to flip them, which makes the integral negative. But then I'm just looking at this area underneath this quarter circle. So that circle having a radius of 3, quarter circle would be pi r squared divided by 4. And then simplifying that a little bit is going to be a -6 minus 9 pi over 4. For g prime of x, we're looking at taking the derivative of g, so the derivative of 2x is 2, but then the derivative of that integral piece, I have to use that second fundamental theorem to say that the derivative of the integral would just be f of x. So I've got 2 plus f of x, and then f prime of -3 would just be plugging in -3 and seeing on my graph that f of -3 is 0. So g prime of -3 is 2. Our next example is a differential equation. Go ahead and try it. So in order to find a particular solution for a differential equation, we're starting with that differential equation and separating our variables. So I would have to divide my w minus 30 to the other side. My 1 over 25 can stay. And then I'm integrating both sides. So on the right, when I integrate with respect to t, I'm just going to get 1 over 25t plus c. But on the left, I would have to use U-substitution. So I use w minus 300 as my u, which makes my du dw. And then I have it in a form that I can integrate and get the natural log of the absolute value of u, which is just the natural log of the absolute value of w minus 300. I do want to change this back because now I'm all in terms of t and not one side in terms of u and the other side in terms of t. With that, we want to do a little bit of finagling. Since this is a natural log equation, in order to get that w by itself, I'm going to need to rewrite this as e to this power equals w minus 300. Which brings us to this point where we're going to need to redefine this c sub 1, which we've talked about before. So because I'm adding that c sub 1 in the power, that's the same as multiplying by e to the c sub 1. And then I'll redefine that e to the c sub 1, since it is also a number, as a c, just a new c value. So once I have my new c value, I'll use that initial condition of 1400, plugging in 0 for t and 1400 for w, which tells me that c is 1100, and then I can put that back into my equation for w of t. If you have a graphing calculator with you, then I do want you to work out this whole problem and see if you can answer this final question, that does the intersection require a traffic signal or not, based on your work. If you do not have a graphing calculator with you, I would at least think through this problem and see what you would be testing in order to determine whether it requires a traffic signal. If you're attempting this without a calculator, I would at least want you to think through the fact that for this product to be over 200,000, the product of cars turning left and cars that are going straight through the intersection, when we have 500 that are going straight through the intersection, means that the cars turning left have to at least be 400 cars in order for it to require a traffic signal. So I'm really trying to decide if there is a 2-hour time interval that has 400 cars at least turning left. And when I look at my graph, I don't want to consider anything that really is not a high rate, because I'm looking for, is there at least one 2-hour time interval that does have that many cars? So I'm looking at this peak here, and it's kind of hard to tell, but I think maybe the highest time interval is from the 14 to 16, or possibly from 13 to 15. So I tried both of them, and if you did have a calculator, this is where you could find that integral from 14 to 16 of L of t using your calculator's definite integration function. And plugging this into your calculator, it says 412.266. If you didn't pick that one, the 13 to 15 integral works as well, and you get over 400 cars there too. And then we would just say, yes, it does need a traffic signal because the product of the left turns and the straight throughs is greater than 200,000 for a certain interval. So we didn't have to do both of those. I was just going to show you both, but you just need one example to say that we need a traffic light.